My name is Omri, and I will be presenting our work on computing functional maps and bases using data-driven approaches. This is a joint work with Ron Gillet from RPI. So we are interested in finding correspondences between shapes. Specifically, these are surfaces, and our aim is to compute a map which aligns every point on one shape to its corresponding point on another shape. Now, this problem tends to be very difficult as a combinatorial problem, and it's typically non-smooth as an optimization problem. Many people in the community, and also us, are using functional maps to compute correspondences between functions instead of points. This allows to design smooth optimization problems, and you can also develop theory that allows you to use additional results from the theory of operator theory or functional analysis to be used in your algorithms. In particular, the functional maps can be viewed as a two-step process. The input to the problem are two matrices where every column of the matrices F1 and F2 is essentially a function, and these pair of functions are aligned. So in particular, the example that you see to the right shows a pair of functions that are aligned, and these will be two columns, one column in F1 and the corresponding column in F2. What we would like to do in functional maps is essentially compute a low rank matrix. Sorry, it will be a full rank matrix, but it will be lower dimensional matrix that aligns these two matrices. And in order to compute this matrix, we will first have to perform a dimensionality reduction step. So this is denoted by the matrices B1 and B2. And we will typically call B1 and B2 basis matrices in the sense that you take the functions in F1 and you project them onto the basis B1. And you do the same on the second shape. And you find this matrix C21 that essentially takes the point cloud on shape 1 to the corresponding point cloud at shape 2. So these are the two steps. Now, essentially, you have freedom to choose the basis as you want. However, typically, people have been using the Plaus-Beltrami operator and its eigenfunctions as the basis. Specifically, now you can see an example of two elements of the spaces on the first shape and the corresponding two elements on the second shape. And you can see that these functions are extremely smooth, and there are a lot of advantages to using these functions. They have a multi-scale nature in the sense that you can sort them and organize them by level of hierarchy. There is a lot of theory of eigenfunctions of Laplace-Beltrami operator in the sense that they span the entire space of functions, and they yield the least error in a bunch of norms, and so on. So this definitely makes a good choice for a basis, and it kind of explains itself why people have been tending to use it for a while. Now, in particular, for the problem that we'll be interested in, there was a prior work by Kovnatsky and others that tried to take the Laplace-Beltrami eigenfunctions, but in addition, they tried to design the basis in the sense that you try to find coefficient matrices Q1 and Q2 such that you try to, in some sense, cherry pick your elements from B1 and similarly from B2. This boils down to an optimization problem that looks as trying to align these point clouds with the additional constraint that you would like the Q matrices, Q1 and Q2, to be orthogonal. And from a functional map perspective, this may be viewed as trying to find a basis such that in that basis the functional map is an identity. And this gives nice results. For instance, the basis elements that you find are actually aligned. Yeah. So for instance, this is an image from the paper. You can see that the eigenfunctions on the first shape are exactly aligned with the eigenfunctions on the second shape. Okay, so this was a work that was done before. Now, one question that we were interested in is, should we actually use the LB basis, in the sense that by the end of the day we get some functions, and these functions are descriptors to the problem. These are in some sense our ground truth. We have multiple ways to represent the functional space on each shape. And Laplace-Beltrami, as I said before, has many good properties, but should we actually use them every time? And we were interested in this question, and this is what we tried to answer in this paper. And one very common choice in other fields mostly is to take a basis which is data-driven. And in particular, POD, or proper orthogonal decomposition, sometimes called PCA, and it is based on the SVD, the singular value decomposition of the matrix. So given a matrix of descriptors, you can compute its SVD. The SVD always exists. And if you take the columns of the matrix U, these are the left singular vectors, and these span the functional space in an hierarchical way, similarly to what happens in LB. So what you see in the figure here are essentially the singular values on the two shapes and how they align with respect to one another. In the sense that if you take only the most dominant singular value or vector, sorry, then it will span a significant chunk of your functional space. And if you take two of them, then they will span. They will also be dominant. So there is a nice hierarchy to the organization of the singular vectors, and you can use them to span your functional space. This is an example on the two shapes that we saw before. You can see that the POD modes are smooth. This is not guaranteed. Basically, it depends on the data. And since the data, the descriptors that I use are smooth, then this is also what I get in the POD modes. But this is not typical. Now, to try to quantify whether this approach might yield something, we were doing the following experiment. We were trying to align the descriptors and try to measure the error in the spectral domain. This is what you see here. And you can see that if you use either LB or POD, you see that you gain several orders of magnitude better error metrics with POD with respect to LB. So we were kind of happy with this. And then we did the same with the spatial error. Essentially, the difference from the left side is that you actually measure with respect to the vertices of the domain and not the modes themselves. And then you see that the figure, the plots kind of switch. So there LB is better. And we were hoping that by designing the bases, we will be able to gain something from this POD. And this is what I will present in the next few slides. So our approach is essentially based on computing 3 or actually 4 matrices, which are based on the functional map and these coefficient matrices. Instead of using LB, we use the POD, and we add regularizing components such as consistency, smoothness, and metric preservation. In practice, it boils down to the following optimization problem, which looks like having an energy term for descriptor consistency, and then an isometric term, which essentially tries to promote the isometric of the map. And then we have another Dirichlet component, which tries to somewhat make the basis elements smooth, because POD does not guarantee it by construction. We additionally have two orthogonal constraints. One is for the coefficient matrices. G is just a mass matrix. And then we also have a consistency between the functional map, because we compute the functional map in one direction and also in the other direction. In practice, this problem is not convex and nonlinear, and it is typically difficult to solve. What we do is we use an ADMM approach. This is an alternating direction method of multipliers. It allows you to split your optimization problem to steps that are easy to solve. In practice, you have an iterative method where at each iteration you solve two Sylvester equations, three linear systems, and you have a trivial update to the dual variables. One way to kind of numerically check that your method does something meaningful is to track various error metrics of ADMM. One is the energy, which is spelled to the left, and you also have a primary residual and the dual residual. In practice, on all the experiments that we used, all of these metrics converge. There is large variation, but we still got convergence, so this is fine. When we go back to the graph that we had before, now we added the designed LB in red and designed POD in purple. And now you see that actually with POD, specifically the design one, in the spatial case, we get the best performance, and in the spectral, it's a moderate benefit over LB. It is not as good as we had with a fixed POD, but it's definitely better than LB. Okay, so now we move to the results. One result that we had in the non-isometric case is to try to align these two shapes. Typically, this is a very difficult problem because we don't know the structure of the functional map itself. Here we show that we are able to get some meaningful correspondence, and the functional map itself, as you can see, even though it is somewhat diagonal, it doesn't have a lot of structure to it. We also stress tested this on larger data sets such as FAUST and SCAPE. We remeshed the meshes, and then we compare against several baseline methods. Our method is the green one. So you can see that we gain some advantage over several methods, and in some cases, the advantages of our method are less prominent. Okay, this is another example where we actually map the texture from one shape to another. This is how the ground truth should look like, and in particular we zoom in on the head, and you can see that in all other methods the head is somewhat mixed. Our approach also mixes some of the details of the texture, but it manages to preserve the center line somewhat nicely. Yeah, and we also compared to the AGD, the work of Kovnatsky and others, and we tried to show that the basis elements that we get are not aligned at all. So if you remember, their work actually got very similar basis components. And this is also can be viewed here. We don't have this restriction. The basis elements can be somewhat arbitrary and do not depend on one another. This is another example to AGD, Kovnatsky et al. And this is an example with a texture transfer, and this is the ground truth. And you can see the differences. This is a challenging example. So our method also struggle, especially in the problematic areas such as the legs. But overall, it gets a better result in comparison to AGD. The final example that I would like to show is with respect to joint quadrangulation. Essentially, you would like to jointly compute quadrangulations of a surface, and basically what we show here is that when you have a fixed LB, the singularities are not aligned, whereas in our method they have better alignment. So to conclude, we show the data-driven approach to design bases. This is in the context of functional map computation. We do a joint optimization for the functional map and for the bases, which is based on an ADMM approach. In the future, we would like to understand better the dependencies between the constraints and the bases, and we also consider the bases design on a single shape. Thank you for your attention.